Welcome all to CIIMAR webinars, and good morning for all of you. So today we have Kasper Hancke, and first of all I want to thank Kasper in the name of CIIMAR for accepting this invitation to talk to us and to whoever is online. So Kasper is a researcher at the Norwegian Institute for Water Research, and he has been working mostly with marine ecology and with photosynthesis in aquatic environments. So he is especially interested in the processes that control the carbon flow and the balance in these phototrophic systems, and how these may be impacted by climate change. He's leading a program about using drones for coastal research, and I think this is what he's going to present us today. And we are very keen to hear your presentation. I would just like to say that at the end we will have some time for questions. So once again, thank you so much, Kasper, and now the floor is yours.
Thank you very much. Thank you again for inviting me to talk for your seminar. I'm Kasper Hancke, and as you say, I'm a researcher at the Norwegian Institute for Water Research in Trondheim. No, sorry, in Oslo, in Norway. I'm a trained marine biologist, and I work a lot with photosynthesis and phototrophic organisms and their role in the carbon flux in coastal systems. Today I will talk on a infrastructure project called SeaBee, which is about drones for the use of environmental research in the coastal zone. I do also have a background in some marine optics and remote sensing, but it is as a marine biologist I have my training. So I'm very glad to get the invitation, and the talk is called SeaBee, simply the Norwegian infrastructure for drone-based research, mapping and monitoring in the coastal zone. Now SeaBee is a large project that is just started. It was funded last year by the Norwegian Research Council, and it's a 5-year project. I is the research leader. And there are 5 research partners in this. There's NIVA is hosting the project, and then there's 5 Norwegian key environmental institutions that is involved in the project. Both biologists, engineers, remote sensing people, and machine learning people, data analysis people, as long as 2 industrial partners, Andøya Space Center and Spectrafly. We also have an data infrastructure provider, which is a national network. It's a rather large project, this one, with a frame of 6 million euros over the next 5 years. Let me give you a little bit about the background, how we got here, and why SeaBee is interesting. So the content and the challenge we are facing today is large. We have a global coastline of about 2.4 million kilometers on the planet. It's around 56 or 58 times around the equator, depending on the resolution, obviously, but this is a good estimate. So there's a lot of coast. 75% of the world population is projected to be living within 100 kilometers from the coast by 2025. I guess for Portugal, that is already the case, and maybe even more than that. Coastal ecosystems are very important in the big picture. 90% of the global fisheries and 80% of known species of marine fish is associated to coastal ecosystems. And kelp forests, which I bring in here because it's one of my own key research topics, and I know you work with it too. It covers about 25% of this global coastline. And along Norway, even Norway has 8,000 square kilometers of kelp forest. Now to the not so funny part. 86% of European coastal ecosystems are threatened. And 1/3 of the coastal region runs a high risk of degradation from infrastructure development and pollution, according to a new UNEP Earthwatch report. So this is obviously important to do something about, and the coast is important to have a good eye on and a data supply from. Now, what we have today is current methods. We have satellites out there in the outer atmosphere. We have small and large research vessels. We have small boats and manual operations. Here's a colleague of mine sitting in a boat on the Norwegian coast, having equipment into the water and measuring, collecting data, writing notes. And we do have divers at the bottom, all at different scales and different perspectives. But we're missing one, because the satellites are of enormous help in these large questions, but they hamper optical disruption in the coastal zone. So there's a large challenge to at all use satellite data in the coastal zone, do some very physical principles. Now, these big research vessels are also good in the big ocean, but they don't go shallow. So everything below 10 meters is not in a focus line. This can go lower or closer to the shore than 10-meter depth, but it's very labor intensive and cumbersome. And this one obviously is limited in its spatial cover. So here comes in drones as a valuable add-on, not replacing any of these, but an add-on that fits a niche and provides us with a high resolution focus on the coastal zone and with a hawk-eye perspective. Now, a bit more specifically on SeaBee. SeaBee is an infrastructure project, so it's not a classic research project. It's more about building an infrastructure that can provide the tools to drive the research. And SeaBee will establish a national center for drone-based services and used in coastal and aquatic research, mapping, and monitoring, as I said already. The primary objective of SeaBee is to deliver a state-of-the-art infrastructure and facilitate exactly research, monitoring, and mapping by using portable, mostly flying, but also surface and underwater drones, combined with machine learning and cloud-based sharing technology. I'll come back to that. Now, to give you just a brief overview of how SeaBee is structured, here are the 7 work packages. It's not so important to you, but it's working on 4 lakes, as I used to say, and I think that's a good way to understand the project. So, and also what it can do, really. So the lake 1 is aerial drones or surface water drones with sophisticated sensors for collecting high resolution data. That is the platform. It doesn't help anything by itself, but it is certainly a tool that we can use. But combining with automated image analysis, semi-automated or at the long run, completely automated analysis based on artificial intelligence algorithms and thematic mappings, we can produce thematic maps of habitats or other things we're interested in and targeted object detection. Now, if we combine this and take it a step further with automated data pipelines for handling and storage of large data sets, but that's what these sensors provide. It's enormous amount of data relative to what we're used to, at least from most of these classical applications. So we need automated systems to handle all these. And least, but certainly important, we need to share those data with the research communities and the end users, the managers, and everybody else. So SeaBee has a large focus on building a cloud-based solution for data sharing to communicate the results directly to stakeholders and researchers and management authorities and so on and so on. That includes you. And SeaBee will provide all its data in the running for free. It will be open access, and everyone can go in through these cloud-based solutions and look at the data, download the data, and also use the data to whatever purpose, as long as the data is cited where it's originated. So that's a bit of the SeaBee background, or how we are structuring this large project. Now, what do we actually do, and how does it work? We work with two different drone systems. Here's or three or four maybe, but the two major ones are fixed wing drones. Here's an example. They're portable. You can bring them into the field easily. You can start them by actually shaking them, as you saw my colleague did here, and you launch it up in the air, and then it goes. All what it does when it flies off is pre-programmed. So once it's in the air, you do not control anything. It's all pre-programmed on a laptop, usually, where you put in the mission planning and you set all the settings. Then you, of course, load the sensors beforehand, and you have your mission and your area ready, and then it takes off and do the job and come back. Same principle with the rotor drones. These are the more known ones. They come small and large. Here's a medium one. Relative to the fixed wing ones, it has a shorter range, but it carry more payload. So this one, for instance, is a DJI M600, and it carries up to 10 kilos. So for very sophisticated sensors, or heavy sensors at least, these are the favorable ones. But they have a shorter range. So if we need large areas covered, we prefer the fixed wing drones. And the fixed wing comes also in different sizes. And one part of SeaBee is working on large fixed wing drones with a wingspan of 2-3 meters, like you see the military applications, in fact. But on the civil side, we have not come very far yet. There's still a lot of engineering to get them to work before we can actually do environmental work on those. So that's the platforms. Now, how does it work on the image analysis side? Ordinary RGB images is easily collected. They come now in very high resolution, and they provide nice pictures from above. But it's hard to quantify images from RGB due to the algorithms that are behind the RGB file format. For that, we have multispectral analysis. It gets more sensitive, and it's also quantitative in a very different way. Here's a SenseFly sensor with 4 bands in the visual spectrum you see there in the middle, and in comparison with the RGB sensor, it sends not the whole spectrum, but some in the blue, some in the green, some of the red light, and some in the near infrared light. And there's a nice illustration down here where we get then data sets of the coast or the area in different color bands. And these are optical correct and can be quantified. Same principle with the satellite remote sensing. Bringing in satellites remote sensing, there's an interesting point here, because there's 40-50 years of research in satellite remote sensing that we, of course, obtain and build on. And a lot of that, the vast majority is based on combining these different spectral bands in algorithms and understand how they relate to each other. For instance, this very common normalized differentiations vegetation index. But machine learning kind of entered the stage recently, and that really puts everything upside down. But we strongly believe that it gives us some new applications that that we didn't have before, but it's also some very new challenges. So I foreseen there's a lot of work in using machine learning to really understand images, but it's surely the way forward. Now a little more specifically, that was sort of the theoretical background and how we can do this. SeaBee, as I said, is not really a research project, but still we have 4 core applications that we focus on. And these 4 are illustrated here. It's water quality and ocean color. It's seafloor habitat characteristics, differentiating different habitats. It's seabird monitoring, and it's marine mammals identification. The later 2 is mostly for population dynamic studies and understanding how these populations in the coastal environments change, move, and what the dynamics are. I will not come much further into that, but the 2 others I'll show you a little more about. Also, terrain modeling is an obvious application that we're working on, and plastic identification or coastal debris mapping and identification. Let me give you a few examples. Here's an applications of eelgrass and seaweed coverage mapping. We have a bay, and it's about 500 meters long. It's 100 meters wide. This is a typical fjord in Norway. It's at the top here, it's meets the beach, meaning 0 water depth. And out here at the southern end, it's about 6-7 meters deep. In between here, there's eelgrass beds, and there's macroalgae beds, and there's sandy sediments, as you see in these light areas. And we want to quantify how much there is of these different ones. So here machine learning is strong, and we made a categorization mosaic. I can say this whole, it's at the top here, this whole image here is based on about 500 single images taken from drones that are stitched together in an RGB mosaic. If we do that with multispectral data as well, we can feed that into machine learning algorithms, and we can set up classifications or habitat classes. For instance, vegetation, beach, rocks, fucus, brown seaweed, sandy sediments, and eelgrass. There's a little overlap here. Don't mind that in this example. But you see the result here is, for instance, focusing on the eelgrass, which is the dark green. It comes out very nice, and it shows a very, very patchy distribution of eelgrass in between sand and brown seaweeds. And it's a good example, I would say, that estimating eelgrass with the traditional ways, where you took video transects, for instance, and you record when eelgrass starts and stops, doesn't at all provide you with this high resolution of how it's really distributed and the dynamics of it. You see, it's quite patchy, and it's very easy from these kinds of images to calculate, for instance, the area of eelgrass in total, if you're interested in that, or in the brown seaweed coverage. And if you do this several times a year or year after year, it's also a very efficient tool to understand the dynamics of these habitats. Yeah, and then of course we classify in building these tools. We do all the manual work as well to understand how good are these predictions, and we produce confusion matrices like this. I don't want to go into the details of how good it is, but in this case it's about 80%. Right. Now here's another application, kelp forests. I know you're interested in that as well, and seaweed mapping. We do this on the Norwegian coast, and you do that on your Portuguese coast. kelp forest is tricky still, but it's something we're working on and trying to identify, if not at species level, at least at group level, and presence absence of kelp forest. And if you see this image here, you see with the naked eye, or you barely see maybe with your naked eye, the brownish coloring of the water, which is kelp forest. And it's these kinds of information that comes very clear out if you start quantifying or putting these sorts of images into machine learning algorithms. Just a few other applications. It's a strong tool to build 3D terrain models. I think you do this as well, those of you that works on drones. This one has a lot of applications. The coastal vegetation and landscape modeling I talked about. We have a sub-program on invasive species detection, and we have something on, we work a little on identification of marine litter or plastics, and we work on improving the recognition and detection algorithm, which is certainly sort of a first step. Now, in summary, very from above, flying drones provide a novel tool in coastal monitoring and mapping. SeaBee specifically, this new project will provide novel solution for research and mapping, management of coastal habitats, animal populations, climate and environmental impacts, and pollution cleanups or guidings of pollution cleanups. With dedicated management and monitoring, we can provide nature-based solutions and proactive climate mitigation actions. That's the bigger goal of it. And last but not least, we're looking forward to continue fruitful collaborations with CIIMAR and other collaborators on future drone research applications. We have already, I can mention, a small ongoing research program with you that we are very happy to participate in. If we have time, I can show a few minutes of this video, or you can yourself look at it on YouTube. You decide that.
I think you can show us, Kasper.
Okay. Let me see if I can do this. Simple. I think I can do like this. You see the NIVA logo now?
Yes.
And
yeah, it. The YouTube.
Yeah, it's a YouTube, so you can see it afterwards. It's just to give you an idea of how we do this in reality, and there's some nice pictures of how it looks in Norway. There's some text there. As I said, it's on YouTube too, and you can revisit it if you like. There's some voiceover and some, but that at least I don't hear that.
We don't hear it either. But
okay, never mind.
The images. You can also share the link if you would like to share the link in the messenger.
Yeah.
Or we'll just search for it. Yeah.
I think it's there. But here's the fixed wing drones. Maybe it flies into the sun here, and it takes a little bit of hardware in the field still, as you can see, to get this up and running. But so still, it's best for nice days. But we're working on Norwegian solutions, weather solutions to that too. Here's an example of how we used these drones to detect plastics of different kinds. And I think I will just stop it there, and you can look at that on YouTube yourself.
Okay.
and
Yes.
yeah.
Okay, so thank you so much, Kasper. It was really great. Oh, wait, just wait. Oh, sorry about that. So I might have some interruption now. Okay, but thank you so much. It was really, really elucidating and really interesting and really important for us. So this is a wonderful tool that I'm sure that we will be able to use and to improve our monitoring and mapping abilities. So I'm very excited to see this presentation, and I'm very excited to see the follow-up of this project.